Hi, I'm Bob. Thank you for joining me in this tutorial on solving the exercises from the textbook Microeconomics Theory and Applications with Calculus, 5th edition by Professor Jeffrey Perloff. Today, we will focus on the Bertrand Oligopoly model. Let's look at exercise 5.1. What happens to the homogeneous good Nash-Bertrand equilibrium price when the number of firms increases, and why? When firms with identical constant marginal costs produce homogeneous products, the Nash-Bertrand equilibrium is the same as the price-taking competitive equilibrium. If the number of firms increases, the result remains unchanged. The firms continue to undercut each other's prices until all firms charge a price equal to their marginal cost, which is identical to the competitive price. The market demand curve determines the market output, which is the competitive quantity. Let's solve exercise 5.2. Will price be lower if duopoly firms set price or if they set quantity? Under what conditions can you give a definite answer to this question? If the firms are identical and produce homogeneous products, the Carnot equilibrium price is higher than the Bertrand equilibrium price. In the Nash-Carnot model, the firms set their quantity simultaneously, and the corresponding equilibrium price will be higher than the firm's marginal cost. By contrast, in the Nash-Bertrand model, the firms set their prices simultaneously, and the equilibrium price equals the firm's marginal cost. However, if the firms produce differentiated products, it is uncertain which model gives a higher equilibrium price. It depends on the demand function each firm faces that summarizes the demand conditions. Let's answer exercise 5.3. Suppose that identical duopoly firms have constant marginal cost of $10 per unit. Firm 1 faces a demand function of Q1 equals 100 minus 2 times P1 plus P2, where Q1 is firm 1's output, P1 is firm 1's price, and P2 is firm 2's price. Similarly, the demand firm 2 faces is Q2 equals 100 minus 2 times P2 plus P1. Solve for the Nash-Bertrand equilibrium. We find the Nash-Bertrand equilibrium in 2 steps. In the first step, we derive each firm's Bertrand best response function. Firm 1 faces a demand function, and we write its profit function. The first-order condition for profit maximization is the marginal derivative of profit with respect to price equals 0. It leads to firm 1's best response function. It tells us the optimal price firm 1 charges, that maximizes its profit for each price firm2 sets. The same approach gives firm2's best response function. We can plot the best response curves in the graph. The curve describes the relationship between prices and has a positive slope. In the second step, the intersection of the two best response curves determines the Nash-Bertrand equilibrium. Solving the two best response functions simultaneously, we obtain the Nash-Bertrand equilibrium prices for the two firms. Each charges $40. Substituting them into each firm's demand function, we find its equilibrium output. Each produces 60 units. The total market output is 120. Let's go to exercise 5.4. Solve for the Nash-Bertrand equilibrium for the firms described in exercise 5.3 if both firms have a marginal cost of $0 per unit. We answer the question using the same approach as in exercise 5.3. In the first step, we find each firm's Bertrand best response function, the optimal price a firm charges to maximize its profit given another firm's price. Firm 1's profit function is as follows. The first-order condition for profit maximization is the partial derivative of profit with respect to price equals 0. It leads to Firm 1's best response function. It indicates how much Firm 1 charges to maximize its profit for each price its rival sets. The Bertrand best response curve has a positive slope. Using the same method, we obtain Firm 2's Bertrand best response function. Firm 1's best response curve shifts down by 5 units compared to that in exercise 5.3. Similarly, Firm 2's best response curve shifts to the left by 5 units. The equilibrium prices at the intersection of the two curves should be lower than those in the last exercise. In the second step, the intersection of the best response curves determines the Nash-Bertrand equilibrium prices. Each firm charges $33.3. The Bertrand equilibrium quantity each firm produces is 66.7 units. The total market output is 133.3 units. As the marginal cost reduces, the Bertrand price falls, and the Bertrand quantity increases. Let's solve exercise 5.5. Solve for the Nash-Bertrand equilibrium for the firms described in exercise 5.3 if Firm 1's marginal cost is $30 per unit and Firm 2's marginal cost is $10 per unit. We use the same approach as in the last two exercises to find the Nash-Bertrand equilibrium. In the first step, we find each firm's Bertrand best response function from the first-order condition for profit maximization. The Bertrand best response curve shows a firm's optimal price it charges to maximize its profit for each price its rival sets. The two Bertrand best response functions are not symmetric because of different marginal costs. We plot the two Bertrand best response curves in the graph. They have positive slopes. In the second step, we find the Nash-Bertrand equilibrium prices by solving the two best response functions simultaneously. Firm 1 charges $50.67 and Firm 2 charges $42.67. Substituting the Bertrand equilibrium prices into each firm's demand function, we obtain the Bertrand quantities. The Bertrand firm with lower marginal cost charges a lower price and produces a higher quantity. Thank you for watching this video and subscribing to my YouTube channel. See you next time.